We discuss in this video about propositions. And we start by defining the alphabet of the variables we can use in the propositions. And I'm going to denote this by Pn to indicate that we have n variables. And I'm going to denote them by x1, x2, all the way to xn. And we are going to define the set of propositions prop in an inductive way in the following way. So prop is defined inductively. As usual, we have to say about the basis. So we will say that really all these variables, they are in themselves propositions. And the second condition, which is the inductive step, is if we have two propositions PQ, then also these ones, P or Q, P and Q, and not P, they are also propositions. And what I would like to do in this video is really to establish the connection between truth functions and propositions. And I'm going to show you that there is an easy way to go from a truth function to a proposition and from a proposition to a truth function. I'm going to discuss first how to go from a proposition to a truth function. So from propositions to truth functions. And what I mean by that is that given a proposition, we can define in a natural way a truth function. And this truth function is going to give a truth value to the proposition you have in your hand. This is going to be called a truth assignment for that proposition. So truth assignment, or we will also call them valuations. And this is defined, since the set of proposition is defined inductively, then obviously also this mapping from propositions to truth functions is also going to be defined inductively. And it's going to be defined in the following way. If I have two propositions P and Q, I denote this valuation by V. So this is going to be V from prop, so from the set of propositions to the set of truth functions. And on the set of variables, I have to define some value. So I'm going to just define whatever values you want to choose for your variables, Vx1, Vx2. So all these are going to be elements of 0, 1. And really, this is going to define the whole mapping of the full proposition. So you can choose these values however way you like. And once we have this, then we are going to think about what was the valuation that we have defined in a previous step for these two propositions in the induction step. So what's the valuation of P and what's the valuation of Q? And there are obviously two possibilities, 0, 1 for V of P and two possibilities for V of Q. So altogether, when we look at all the combinations we have for possibilities, and according to our inductive definition, we have to define what's the valuation for each one of these four cases, what's the valuation for this proposition, what's the valuation for that proposition, and then we also think about this unary operator. So in this case, I'm going to define v of p or q, and I'm going to define v of p and q. And as you can imagine, based on your intuition with logical formulas, the valuation of p or q, in this case, if the valuation of p and q was 0, so the valuation of the disjunction is going to be 0, and it's going to be 1 in all the other cases, because at least one of them, in the last case both of them, is equal to 1. And with a similar intuition, the valuation we give for the conjunction is going to be 0 in these three cases, because at least one of them is 0 or false, and it's going to be 1 or 2, if you like, in this last case, because they are both equal to 1. And the valuation for the negation is going to be defined depending on just what the valuation of p is. Obviously, we only have two possibilities for the valuation of p. It's either 0 or 1. And we define the valuation of non-p to be 1 in this case when v of p is 0, and 0 in the case of v of p is 1. So in this way, starting from whichever valuations we want to give to these variables, whether it's 0 or 1, then we build up inductively a valuation for any proposition. In other words, we manage to define a way to go from propositions to truth functions. Now, there is one concept that I can define now in this context once we have the mapping from proposition to truth functions defined, and that is the concept of logical equivalence. And this, I'm going to use the symbol with 3 horizontal bars. And we will say that two propositions are said to be equivalent, and we denote this by P concurrent or P equivalent to Q, if, and here is the valuation of P is equal to the valuation of Q for all possible valuations in nu n. So, in other words, our propositions are going to be equivalent if the truth functions that we associate to them are exactly the same. So, in the truth table, all the values are the same for each entry in that truth table. So with this, we have a way, I'm going to come back to this notion of logical equivalence. So in this way, we have defined how to go from propositions to truth functions. So now we'd like to discuss how to go back from truth functions to propositions. And to do that, I'm going to have a discussion in 2 steps. So remember that a truth function phi is really a function that is defined on nu n, which was the set of vectors of dimension n with 0, 1 on each entry, and this was taking value in 0, 1. And really, a truth function can be defined via truth table. So we can think about this truth function as being given by such a truth table. And in this truth table, we have to define what's the value for all possible combinations of V. And we have the first one where all of the components, all the n components are equal to 0. And let's say that this is vector V0. Then we have the next one where all of them are 0 except the last one being 1, and let's say we denote this by v1. And we have the next one where this one is 1 and all the other ones are 0. And say I'm writing just one more, maybe this is going to be the next one, and so on, all the way to, and the last one, in this set we have exactly 2 to the power n elements, so the last one is going to be vector 2 to the power n minus 1, which is really going to be that vector that has all the entries, all the n entries equal to 1. And so there is a value, a truth function is given by what value this function takes for each one of these vectors. So the truth function is defined by these values. What is phi of v0, and what is phi of v1, phi of v2, phi of v3, and so on. So we have to know the values for each one of these vectors. And so, given such a truth function, given such a truth table, if you like, I would like to build a proposition that, in some sense, captures the essence, in a way that I'm going to define in a moment, the essence of this truth function. And I would like to do this in 2 steps. The preliminary step I do in my discussion is I want to give a name to each one of these components, and I'm going to give them a name in terms of variables. I'm going to define a variable for each one of these components. I'm going to say that for this component of the vectors, this is going to correspond to variable, say, x1. This is going to correspond to variable x2, and so on. We have n columns, so we have n variables. And I'm going to use these variables to define the proposition corresponding to this truth function. And so I do this construction in 2 steps. The first step, in fact, I'm going to ignore this for a second. So for a second, I'm going to say ignore this. Ignore the values that the truth function gets, and let's focus just on this part. In other words, focus on some sort of an encoding. I would like to have a proposition that describes, using the language of propositions, I would like to describe what this vector is. And I'm going to do it in the following way. I'm going to say that for each v, I'm going to define a proposition p of v. I'm going to define it in the following way. If my vector v is made of values, say, a1, a2, an, this is going to correspond to proposition p of v, where I'm going to first write it and then explain what I'm writing. I'm going to have variable x1, and I will define this in a moment. What do I mean by this exponent? But it's going to be something like variable x1 and variable x2 and variable xn. And what I mean by this notation, so I'm going to define this, a variable xi to power 1 is going to be xi, and the xi to power 0 is going to be not xi. And so really what I want to define in here is that I would like to describe the 0 and 1 elements of this vector in the form of a proposition. So whenever I see a 1 in here, if there was a 1 in here, I'm going to denote that by x1, because it says I have a 1 in here, so I'm going to denote that by x1. If there was a 0 in this component, I'm going to have not x2, which is going to indicate that this proposition only becomes true when this x2 is 0, exactly how the vector was on this component. I give one example to make things concrete. So if I take, so if I'm writing here an example, maybe here. So example, if I have, say, a vector of 2 components, and all the 4 possibilities are these ones. So that's the vector v in here, and that's the proposition I want to build, P of v. This corresponds to variable x1, and this corresponds to x2. So what I'm writing in here is I want to describe in the form of a proposition that both of these components are x0, are equal to 0. So what I'm writing is not x1. So when I have a 0, I'm going to write not the variable corresponding to this, and because this one is 0, I'm going to write not x2. In this case, this one is 0, so it's going to be not x1 and x2 because I see 1 on this component. This vector is going to correspond x1 and, because this one is 0, it's going to be not x2. And because I have 1 here, this is going to correspond to proposition x1 and x2. And essentially that's what I wanted to define here on a general level. So for vectors of any dimension, I can have this definition where essentially I'm describing through a proposition what are the entries 0 or 1 of this vector. And once again, the idea is when I see it's going to be a big conjunction, and if I see a 0 on component I, I'm going to place here not xi in this conjunction. If I see a 1 on component I, then it's going to be xi on that big conjunction that I define in here. So that's the first step I wanted to have for my construction. And once I have this, then now I can define really my goal, which was from truth functions to propositions. So I can really define the proposition associated to phi. So phi was given by this truth table. So I can now define P of phi. So in general, from a truth function phi, I will go to pi of phi. And this is going to be described in the following. I'm writing first and then I explain. So this is going to be a big disjunction, and this is going to be a disjunction by all the vectors v with the property that phi of v equal 1. So essentially I'm going to look on the value of the function phi, and wherever I see a 1, I will have an entry in this big disjunction for that element, and the element that corresponds in this disjunction is going to be simply P of v. So in other words, what I'm doing is for this truth table, for this truth function, I'm going to check where do I have a 1, and where I see a 1, I'm going to have one element in this disjunction. So it's going to be some proposition formula corresponding to this one, or something corresponding to this one, or something corresponding to this one. And I do this for all the ones in the truth values. And the components that I'm writing is the description of the corresponding vector. So it's exactly this P of v that I just defined. So I give an example now. I just continue here with this example. So if, let's say, my truth function was defined, I just give some arbitrary values. For example, if it was defined like this, it's 1 for 0, 0, and it's 0 for 0, 1. And let's say it was 1 for 1, 0, and let's say that it was 0 for this one. Then the proposition I associate to this particular truth function is going to be pi P of phi. And it's going to be, I'm going to collect in a disjunction something corresponding to this one and something corresponding to this one. So it's going to be something, and I come back to this in a moment. What is that something? But this is going to correspond to this one, disjunction with something corresponding to this one. And what I'm writing here is exactly this description of vector z0. So I'm going to write exactly this, not x1 and not x2. And for this one, I'm going to write this. So it's going to be x1 and not x2. And so in general, this is going to be the proposition associated to phi. It's a big disjunction over all the vectors having value phi of v equal 1 of the propositional encoding of the vector v, p of v, which we have just described in the previous steps. So with these two constructions, we can in fact formulate, we can formulate a lemma, and in fact, the lemma is already proved based on this whole discussion we had. And the lemma is to every truth function corresponds a proposition. And we have discussed a way to actually build this, and the other part of the lemma is to every proposition corresponds a truth function, and remember that we call this the valuation of that proposition, and we showed how to build it. So what I still want to do is I want to define two special propositions. And those two special propositions are going to be denoted, somehow overloading the notation I had in a previous lecture. I'm going to use these two symbols. And this one is going to be the truth function. So the true function, always true function, if you like, or always true proposition. And that's the intuition you should have. And this one, if you like, the intuition you should have is the always false proposition. So these are just two special propositions I'm defining. And so now the observation I want to make is that really based on the discussion we had so far, it's already clear that this particular set, so prop, this is a set of propositions modulo logical equivalence. So the idea being that when you have two propositions that are logically equivalent in this set, they are identical. They are just represented by one single element in this set. So this set, if we do disjunction, conjunction, negation, and I'm also adding the always false and the always true special propositions, this is a Boolean algebra. So I leave this lemma without a proof. It's also left without proofs in your lecture notes, and I'm just making the point that somehow it's already implicit in all these arguments we have listed before. Now, the point that I do want to make here is that it's really this prop equivalent that's a Boolean algebra, and in fact, you should observe that the set of propositions with all these operations, if you like, the set of proposition is not a Boolean algebra. And it doesn't look like a big difference between prop and prop equivalent, maybe. But the point is that, for example, in the set of prop, for example, if I have a variable x1 and I say, you know, I take this proposition x1 and not x1, that's certainly, I'm sorry, x1. So that's a proposition. And in fact, if I take variable x2 and not x2, that's also a proposition. But in fact, in prop equivalent, these two propositions are seen to be equivalent. They have exactly the same value for all possible valuations of x1 and x2. And in fact, x1 and not x2, not x1, is equivalent to x2 and not x2. And in fact, they are equivalent with the always false proposition. My point here being that this cannot be a Boolean algebra, because in that sense you would have two zero elements. This would be a zero element and that would be a zero element. And it can be proved that in a Boolean algebra, the zero element and in fact also the one element is unique. So really, this is one argument, and you can also have other arguments for why prop is not a Boolean algebra, but prop equivalent is indeed a Boolean algebra. Now, the moment we have established that the set of propositions, modulo equivalence, is a Boolean algebra, then automatically all these properties that we have proved in previous lectures about Boolean algebras, they also apply to propositions. So for example, so I'm writing here all properties of Boolean algebras apply also to prop equivalent. And for example, the so-called De Morgan properties. So this is just one example. The De Morgan properties, they do apply to propositions modulo equivalence, meaning that we already, just by showing that this is a Boolean algebra, we have already established that this general property of Boolean algebra, which is not P or Q, this is in fact the same object. In other words, it's equivalent with the proposition not P and not Q. And also the other one is not P and Q. This is equivalent with not P or not Q. And so you should check these De Morgan properties. We had them in lemma 2.7. Where we show that in fact these properties hold in general for any Boolean algebra, so in particular also for the propositions modulo equivalence. There is only one more point I want to make, and that is if it happens so that we have no variables. So if really n equals 0, or if you like, another way of saying is the set of variables is the empty set. And really that means that here in the set of propositions we really only have these constant propositions. There is nothing else. All the other propositions, they would have to be built based on variables, but we have no variables in this example I want to make. And so in this case we have a Boolean algebra corresponding to this prop modulo equivalence, which consists of just two elements, and I'm going to denote this by B2. And this is going to be made of just two single objects, the always false and the always true function, and I'm going to just denote them by 0 and 1. I could also just continue using these two elements, but later on it's going to be useful to think about them as 0 and 1s, and indeed this is the 0 element of this Boolean algebra, and that's the 1 element of this Boolean algebra. So 0 and 1, and I'm also changing slightly the notation. This is going to be useful later on. Instead of the disjunction, I'm going to denote it by plus, and instead of conjunction, I'm going to denote it by dot. And I'm also making the observation that really I can, instead of negation, write this element, this operation minus, and that's a 0 element, that's a 1 element. So really the Boolean algebra becomes this one. And just to write the definition of disjunction and conjunctions in terms of plus and dot, so just to remind what these operations are. So when I'm applying plus, or as it was before, disjunction on 0 and 1, then this is going to be defined as 0, 1, and 1, and 1. So this is exactly the same as we had before, but now just using this notation of plus and multiplication. And in terms of multiplication, or as we had before, conjunction, this is defined as 0, 0 in this case, and just 1 in this corner. And the minus is going to be, this is applied just to one operator. So the minus in the case of 0, that's going to become a 1. And in case of 1, this becomes 0. So when you look at this, this is going to correspond very well to your typical operations on 0 and 1, so addition and multiplication, with the only exception being this element where 1 plus 1 is not what you would normally think about in terms of, for example, modulo 2 calculations, but 1 plus 1 in this case is equal to 1.